Hello, this is Jake Abbott. In this video, we're going to be talking about state feedback. Up until this point in this course, everything we've been talking about is characterizing linear systems, and mainly we've been focusing on linear time invariant systems. But it's all about characterization. You're given some system and you talk about what is its transient response, what is its stability properties, is it controllable, is it observable? But we've never actually tried to change the system. We've just characterized the system we've been given. But ultimately, that's what control systems is about, is changing the system, making it have the properties we want it to have. And so this is going to be the first lecture where we actually start to do that, and we're going to be doing it by closing the loop using state feedback. So we're going to be talking about a linear system that's a single input, single output system for now. So we can have n states, so this is some n by 1 vector, but we're going to assume we have just one input. So let's say this is n by n, this is n by 1, this is n by 1, this is 1 by 1, and then we have one output as well. So this is 1 by n and n by 1. So we're going to be talking about these single input, single output systems, and we're going to start from the assumption that our system is controllable. And so if you remember, we talk about writing that the pair AB is controllable. And we're going to start from that assumption in all of our discussion today. And if we remember what the fundamental definition of controllable is it says if we have some initial state and we have some desired state that we want to move to, then there exists some input u that will move us from that initial state to that final state, and it will only take finite time. But we know if our system is controllable, we know that u will exist, but we've never actually talked about how to make that u. And so this we're going to discuss one possible way that you can do that in this video today. So to begin, let's review the idea of controllable canonical form. So if we have a system that we know is controllable, then we have shown before that we can convert that system. I'm gonna assume that I have a 3 by 3 system for this whole lecture, but the results apply to general n by n systems, and I believe the textbook uses a 4 by 4 system, so you can compare the difference. So we can always take our original system and transform it into what we call the controllable canonical form. And we've seen this before. I'll put a tilde over this new system. It's just a transformation, equivalence transformation. And so it looks something like this: minus alpha 1, minus alpha 2, minus alpha 3, and then I have a 1 here and here. And this is my new state vector, which is this tilde state vector, plus the vector 1, 0, 0 times u. And this is based on our characteristic equation of our original system, looked like s cubed plus alpha 1 s squared plus alpha 2 s plus alpha. So anytime our system is controllable, then there's some equivalence transformation that will get us into this form. And we call it the controllable canonical form. And it's nice because you just see the coefficients of the characteristic equation built right into the A matrix in this form. And so that's going to be some similarity transformation to get to this, which is going to look like some p times our original x. So we're going to multiply our original x by some p, and it's an invertible p, and we'll get to this new state transformation. And so there's actually a form we found to get into this, and the way we can do that is we can solve for p inverse like this, where we use the controllability matrix itself. So in this case, that will look like this. And we multiply that by this form, which look like 1's on the diagonal, and then alpha 1's on the superdiagonal, and alpha 2 on the next superdiagonal. And if you had bigger things, you'd have alpha 3 on the next superdiagonal. And so if we if we build up a P inverse matrix in this form and then invert that matrix, we get a P, and that transformation will move us from our original totally arbitrary A and B matrix to this new controllable canonical form. And this definitely is always going to exist. You can see that this is a full rank matrix because it's upper triangular and it's all ones on the diagonal. So the eigenvalues of this 3 by 3 matrix are all ones. So we know this is an invertible full rank matrix. We've already established that we're only considering controllable systems, so then this controllability matrix is also full rank, and we know it's square, it's 3 by 3 because this is a single input, single output system, so each of these columns is a 3 by 1 thing. So we have a 3 by 3 full rank matrix times a 3 by 3 full rank matrix, and so the thing we get out is a 3 by 3 full rank matrix. So this thing is definitely invertible, and so we can define it like this, and when we invert it, that's P. So any system that's controllable, by using this transformation, we can convert it into its controllable canonical form. So that's established at this point. The next thing I want to review really quickly, this just to sort of build on these ideas, is that the eigenvalues are uniquely locked up in the coefficients of that characteristic polynomial. So like for example, let's say we know our eigenvalues are lambda 1 and lambda 2 and lambda 3. So this is our characteristic equation. And if we actually do that, we've done this math before at some point, and we can, I'm just going to skip all the algebra and cut to the solution. We get something like this, where we have lambda 1 plus lambda 2 plus lambda 3 in front of s squared, and then we have a lambda 1 lambda 2 and a lambda 1 lambda 3 and a lambda 2 lambda 3. So all of those different combinations times s, and then minus lambda 1 lambda 2 lambda 3. So if you do this multiplication, you get something like this, and we know that this is going to end up equaling something like some alpha 1 s squared plus some alpha 2 s plus some alpha 3. And so we basically have three equations and three unknowns, where this is our alpha 3 and this is our alpha 2. And so you can kind of think of this both ways. You can say, if I'm given three eigenvalues, I can actually explicitly multiply this out and figure out my relationships between my eigenvalues and my alphas. Or you can think of it the other way and say, if I'm given some characteristic polynomial, I know its roots, which are unique. If I ask you find the roots of this, you can find them for me. There's one unique solution. Those roots are the eigenvalues. So there's this one-to-one mapping between the eigenvalues of our system and the coefficients of our characteristic polynomial. So now we have these two ideas in our head, that if we understand the characteristic polynomial, we understand the eigenvalues, and vice versa, and that if our system is controllable, then we can always convert it into a controllable canonical form. Okay, with that established, for now on, let's start considering systems that are in the controllable canonical form. Now what we're going to do is we're going to try and implement state feedback. And this is just something that's a clever thing that someone tried, and it works really beautifully. So let's see the result. So what we're going to do is we're going to start with our original system, ax plus bu, y equals cx, and our system's already in controllable canonical form, but we'll come back to that in just a second, but for now we don't actually need to have that information. And so what we're going to do here at this point, our u is our system input. And so what you should be imagining here when I say system input is something like, maybe the thing we want to control is a velocity. That's what y is. But u is something like a voltage. So it's not necessarily something that you know how it directly maps to your output. It's not like u is some desired velocity. U is like a voltage or something, and y is some velocity. So it's this interesting problem where if I'm designing a cruise control for a car, and I say, what should my controller be to control the acceleration, the accelerator pedal, for a given velocity? Should I push it down 1 inch? Should I push it down 1.5 inches? It's a very unintuitive way to look at things. In reality, the way you would look at a problem like that is you say, how much should I push down the accelerator to go 50 miles an hour? Your answer would be something like, well, push it down as much as you need to push it down to make the car go 50 miles an hour. So that's this idea of closed loop control, is we're going to start establishing our control objectives in terms of the desired output, and then we'll let U be whatever it needs to be to accomplish that goal. And so one simple way we could propose to set U is we could say, let's set U equal to some other variable, which we'll call R, minus K times X. So U we've already said is a 1 by 1 thing, and to make these add up, R must be a 1 by 1 thing. And we know X is an n by 1 thing, so this K matrix must be a 1 by n thing. So it's going to look something like this. U is going to equal R minus, I'll break K up into its little subcomponents, so K1 through Kn, and then times the X vector. And so there's going to be n real numbers in this matrix, and we have to establish what those are. But if I were to plug this U equation into our original equation, what I get is x dot equals ax plus b r, I'm plugging in this U in here, minus b k x. And if I group the x terms together, I get a minus bk times x plus br. And so I have this new state equation by setting U equal to some other reference signal R minus K times X. I've created a new system with a new A matrix, which now looks like A minus BK, and a new B matrix, which is the same B. So I didn't change the B matrix, but I changed my A matrix. And we know from all the system analysis that we've been doing this semester, we know that the A matrix is the matrix that describes our system's stability and our system's transient response. So we've just messed with our system's stability and transient response. We haven't said how we've messed with it yet, but we've messed with it. So we've created this new system that behaves differently than the old system by implementing this sort of feedback routine. So the question is, how does this system behave? Well, one thing that we should note, just so it doesn't go without being said, is that it turns out if the pair AB is controllable, sorry for my bad handwriting, I'm just writing fast because it's not important. If AB is controllable, we also know that this pair A minus BK B is controllable. And it's a controllable. So these two things are equivalent statements. So our original system, we said there must exist some U that can drive our system from some initial state to some final state. Now we can say there must exist some R that will drive our new system from some initial state to some desired state. So we haven't changed our controllability of our system at all by doing this thing, which makes sense because, we still really ultimately have just this U to move around. And so all we're doing is putting some rules on how we move U, but we haven't fundamentally affected our controllability. So if we explicitly go through and plug in this K matrix and figure out what our new system looks like, it's very enlightening in what we see. So if we do that, if we say A minus BK, where our A matrix, we've said we already are in controllable canonical form. So we have minus alpha 1, minus alpha 2, minus alpha 3. And remember, any system can be converted into a controllable and canonical form, so I haven't lost any generality by assuming I'm in this form. And my B in controllable canonical form looks like 1, 0, 0. And my K now looks like K1, K2, K3, because I have a 3 by 3 system I'm considering. And I explicitly do this math of this, I get something that looks like K1, K2, K3, and then these are all zeros. And then if I take this matrix and subtract that matrix, what I get is something that looks like minus, and I'll group these things, alpha 1 plus k1, and minus alpha 2 plus k2, and minus alpha 3 plus k3, and I get a 1, 0, 0, 1, 0, 0. And I realize that after I do this, my new matrix, this is my new A matrix, which equals A minus BK, my new matrix is also in controllable canonical form. And it's in controllable canonical form of this new system whose characteristic equation now looks like s cubed plus alpha 1 plus k1 s squared plus alpha 2 plus k2 s plus alpha 3 plus k3. And so this is this new system with a new characteristic equation, and because we can make k1, k2, and k3 anything we want, we can take any sort of desired characteristic equation, like this, it's alpha 2 tilde plus some alpha 3 tilde. We can take any desired characteristic equation of this form and we can achieve it because we can make k1 anything we want. So it doesn't even matter what alpha 1 is. I can make this new alpha 1 whatever I want because I have control of k1, and these are all decoupled from each other. So basically, I can take my original system that has some characteristic equation that may or may not be desirable, it may not be stable, it may have really bad transient properties, and by setting k1, k2, and k3, I'll make this new system that has this characteristic equation, and I can make its values whatever I want. And the solution for those k's is really straightforward, right? Because those are really simple equations that we had. So you end up just saying, well, what should k1 equal? It should equal my alpha 1 tilde minus my alpha 1. So my desired alpha 1 minus my actual alpha 1. And I just proceed with this sort of routine. So I say k2 should equal alpha 2 tilde minus alpha 2. And you go down the line like that. And so it's really straightforward. And if we remember, we started with this notion that our system was already in controllable canonical form. So let's say that this matrix, this K matrix that we just filled out was K tilde. We were in controllable canonical form, and we made this K tilde, which was equal to our K1 and our K2 and our K3 that we just solved. Now, our original system, let's relax that assumption that it was given to us in controllable canonical form. Let's say our original system wasn't given to us in controllable canonical form, and we did this transformation, P, to get it into controllable canonical form that we discussed at the beginning of this video. Then our final step is we convert our system to controllable canonical form, we solve for the k's in this way, we build this K tilde matrix using that, and then the last step is we say that K is equal to K tilde times P. So we basically map our system into controllable canonical form, solve for the K's that we want in that realm, and then map it back. So we take that K, those K's we solve for, and map it back to our original system that wasn't in controllable canonical form. And when we're done with that, if we take our original A and we minus BK, we'll get this new A matrix that has the eigenvalues and characteristic equation that we wanted. So we have complete control over this. So I'm just going to summarize really quickly kind of the logic of this. If we start with our system being controllable, so we have some pair AB and it's controllable, then the idea that follows from that is our system is similar to a controllable canonical form. So our system's controllable, then we know it's similar to a controllable canonical form. If we know it's similar to a controllable canonical form, we can set the characteristic equation, using state feedback. And if we can set the characteristic equation, then that means we can set the system eigenvalues to be whatever we want. So this is sort of the fundamental result of controllability that we were getting to all this time. And when we define controllability, we defined it as that there exists some input u to drive us from any desired state to any final state in finite time. But we didn't know how to choose u, and it wasn't a super useful result for us. We just knew it would exist. But in practice, what we find is that if our system is controllable, then we can, through state feedback, set our system eigenvalues wherever we want. And I hope with all of our discussion that we've had about stability and time response, you see how important this is, that our ability to set the eigenvalues wherever we want them is a very powerful result, and that is the result of state feedback.